Hello wonderful person, this is Anton, and today we're going to discuss some of the major breakthroughs when it comes to observing one of the biggest mysteries in the universe, the now famous dark matter, but specifically because of some of the more recent observations using the James Webb Space Telescope. And so here, based on the 2026 study, we now have a new understanding of this invisible scaffolding that seems to hold our universe together. But just so that we're clear, it's still kind of mysterious. We actually still have no idea exactly what it's made out of. The only thing we know for sure is that there seems to be something there, because otherwise it's impossible to explain these very specific observations we're going to be discussing today. And in some sense, the observations in this study can actually be kind of compared to, I guess, observing and measuring the wind by looking at how the trees move and sway in the forest. And so even though we don't really see the wind, we know it's there. And so here, thanks to some of the more recent observations, researchers have produced the most detailed and high-resolution map of the mysterious dark matter. And right now this is one of the best maps we seem to have. But to understand why this is important and what this tells us about the universe, let's I guess briefly take a look at what we already know. And so I guess let's briefly discuss the important facts about dark matter that you need to know to understand this discovery. And well, fact number one is that the ordinary matter, the stuff we're made out of, seems to be only about 1/6 of everything, or 1/6 of all matter in the universe. And the rest seems to be more or less invisible and does not seem to produce electromagnetic emissions. And so this elusive substance that doesn't emit, absorb, or reflect light is what scientists refer to as dark matter. But it's not completely invisible because it does produce gravitational effects, and because of this, its presence can be determined by observing gravitational lensing effects like the one you see right here. The fact that these galaxies are so warped and the fact that this produces such a powerful lens cannot be explained if it wasn't for dark matter. And so here it seems to produce an enormous gravitational pull. And this bizarre invisible glue is also important to explain the existence of many different galaxies and galactic clusters. And that's because without it, galaxies like the Milky Way or some of the clusters known to us would simply spin themselves apart just because things in them move really fast. And so overall, it seems to act as a kind of a gravitational backbone that shapes the formation of everything we see around us. And in some sense, it might resemble something like this, with each of those lights you see, those being galaxies and galactic clusters. But in this new study from January of 2026, an international team led by researchers from Durham University and the NASA's Jet Propulsion Lab revealed a new high-resolution map of dark matter in the region of the sky known as the Cosmos Field, also known as the Cosmic Evolution Survey Deep Field, representing individual staged photographs initially taken by the Hubble Space Telescope between 2003 and 2005. In a nutshell, it kinda looks like this. This is a mosaic of 575 individual images. And this field, located in the constellation of Sextans, represents an area in the night skies approximately 2.5 times larger than the full moon and has been studied for decades. It's probably one of the most studied regions in the night skies, at least in the last 2 decades. But this time, instead of using Hubble, the team used the James Webb Space Telescope. And so by conducting 250 hours of observations, they were able to discover a lot of new things. And first of all, in this tiny patch of night skies, they saw approximately 800,000 different galaxies. And many of them have never been seen before and were only visible to the James Webb. But, importantly, by analyzing these galaxies, they then created a map that is twice as sharp as previous maps created by the Hubble Space Telescope. And more importantly for cosmology, this allowed them to create a distribution map of dark matter. But I guess one important question is, how? It's supposed to be invisible. Well, for this, researchers used a very famous technique referred to as weak gravitational lensing. And in this case, this is done by looking at extremely distant galaxies and then observing very minor changes in their shape and the overall warping, and then basically comparing this to what we expect. Or to be more exact, the light from these distant galaxies doesn't travel in a straight line, and instead it gets bent and distorted by gravity of dark matter located between us and a lot of these distant galaxies. And so by measuring these very tiny distortions, sometimes as small as 1%, generally scientists learn how to calculate the amount of dark matter present in a certain region. And this is mostly done by comparing the assumed shape of the galaxy with what's being observed. And so because many of these background galaxies usually appear slightly smudged or slightly stretched, scientists break down these effects into 2 components: the shear or the stretching effect and the convergence or the magnification effect. And though this will be difficult to achieve for a single galaxy because maybe this galaxy just looks weird, by looking at hundreds and even thousands of galaxies and using statistical methods, it then becomes possible to work out what most of them are supposed to look like and what they seem to look like because of gravitational effects. And while James Webb seems to be well suited for this because it can easily resolve the shapes of 130 galaxies per square arc minute. And that's nearly double the capacity of the Hubble telescope, which then allows for an extremely high spatial resolution, revealing fine-grained structures that were previously blurry or even invisible. And that's essentially how they were then able to create this. And this is the comparison of the same image from the Hubble and the Webb. The one on the left is from 2007. And as you can see in this description, one of the more exciting discoveries here is the visible confirmation for the thin filament of the cosmic web, the spiderweb-like structure that the entire universe seems to contain. But one of the more significant discoveries in this case is the confirmation that dark matter and regular matter seem to have evolved and grew up together. Or basically the map seems to show an almost perfect overlap between ordinary matter and dark matter. Wherever there is a massive cluster of thousands of galaxies, there is an equally massive clump of dark matter. And that's of course a major confirmation for some of the modern predictions from the Lambda CDM model. Likewise, as I mentioned, there's a major confirmation for the filamentary structures, the bridges of dark matter that seem to connect a lot of clusters together. This is of course the famous cosmic web. You can learn about some of the recent discoveries in some of the videos in the description, but this is probably one of the best confirmations we have for its existence. But interestingly, this study also discovered some of these unusual mass peaks that seem to have no clear counterparts in the luminous galaxies or hot gas. And that is a really exciting discovery because it essentially suggests structures that are almost entirely dominated by dark matter. And this supports one of the recent discoveries of these dark galaxies that we've discussed in one of the videos in the description. Basically galaxies that never became galaxies, but only contain dark matter and a little bit of gas. Interestingly, as you can see in this image, this was only visible to the James Webb, but not to Hubble. And on top of this, compared to the Hubble telescope, this new project was also able to see much farther back in time. Here it captures this mass imprint going back to about redshift of 2, corresponding to an era known as the cosmic noon. This was the peak epoch of star formation when the universe was extremely bright, which was approximately 10 to 11 billion years ago. So this doesn't go all the way to the edge of the universe, but it goes to some of the more important parts. As a matter of fact, here it can even see very unusual significant structures at redshift of 1.1, which have never been seen before. But obviously at this point, it's not entirely clear what produces some of these structures. But I guess one question here is, okay, so why is this important? Well, this isn't just about distant galaxies, it is also about our own existence. And that's because a lot of current theories do suggest that in the early universe, everything was essentially clumping around these dark matter chunks that started to form this early cosmic web. And it was this cosmic web and all of these initial clumps that then started to pull ordinary matter, eventually creating dense regions where stars and galaxies finally started to form. Or basically everything seems to have started with this dark matter web. And without it, stars and galaxies may not even exist, or would have existed much later and looked and behaved very differently. And so dark matter potentially accelerated the entire process in the universe, eventually allowing galaxies to evolve pretty quickly and basically produce heavier and heavier elements, with some of them, like carbon and oxygen, at some point creating terrestrial planets, and ultimately life itself. And so in a very real sense, dark matter is the architect that allowed the conditions for life to emerge. Or at least that's, I guess, one way of seeing why this is important. But as impressive as this map is, right now it only covers a very small corner of the universe. And looking ahead, researchers plan to expand these maps using some of the upcoming missions, like the ESA's Euclid telescope you can learn about in the video in the description, or NASA's Nancy Grace Roman telescope that we'll discuss during one of the live streams on the channel. And well, the goal is to basically create bigger maps and to eventually try to cover the area that's at least 4,000 times larger than this cosmos region right here. And by doing so, we can then start answering the questions of how some of this changed through cosmic history, and if dark matter, and by extension the universe, seems to be the same everywhere. And while the current data and most of the discoveries from this study seem to match the current model referred to as lambda CDM, one of the main points for many of these studies, and one of the main goals, is to actually try to find small discrepancies, or I guess small anomalies, that might help us understand the universe a little bit better, possibly reveal new physics, or possibly explain some of the anomalies that are still not explained. Which means that we'll definitely come back and discuss this more in some of the future videos once there are some additional discoveries. But on that note, check out some of the previous videos, including videos on dark matter, in some of the links in the description. Thank you for watching, subscribe, come back tomorrow to learn something else, support the channel on Patreon where you can find additional videos without any ads and can DM me directly, or by joining the channel membership that grants you early access, and a few more things. You can also support this channel by buying the Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.